Hello, this is Kenneth Wong, Senior Editor for DE, Digital Engineering Magazine. Welcome to another episode of our Hot Seat webcast, where we put cutting-edge technologies into the hot seat, as it were, to see if they can stand up to a good grilling. Let's start. But today's episode is sponsored by MSC Software, Ultimaker, and Focus 3D. So thanks to our sponsors for making this event possible. Now, before we go to the event itself, a few housekeeping items, if I may. Before we begin, I want to remind everyone that if you have questions for the panelists, you can submit them in the Q&A box at any time. We'll address them in the Q&A session after the presentations, and we'll get through as many as time permits. You can also download a PDF copy of today's slides and check out the resources related to the topic from the resource list to the left side of your window. If you are experiencing any technical problems, please visit the webcast help guide by clicking on the help icon at the bottom of the console. If the slides are not advancing, you might want to try pressing F5 and refresh your browser. That usually solves a lot of the problem. That's all for the housekeeping, so let's talk about today's topic, shall we? During the COVID-related shutdowns, additive manufacturing, or 3D printing as it's more widely known, step up to fill the gaps from suspended factory operations, proving it can be more than a prototyping technology. But how sustainable is 3D printing as a means of mass production for the long run? To answer that, we're going to put AM hardware and software under the hot seat today. So let's meet our panelists. The first panelist we have is Jeff Robertson from MSC Software. Jeff, welcome. Would you do your self-introduction and give us your opening remarks, please? Your time is 3 minutes for opening remarks, sir.
Thank you, Ken. As you mentioned, my name is Jeff Robertson, Business Development from Simufect Engineering and Forming Technologies. Simufect and Forming Technologies are part of MSC Software, which is a full-range CAE provider, leveraging all sorts of CAE solutions across the full range. In addition, MSC Software is part of Hexagon Manufacturing Intelligence. And so Hexagon, which covers metrology equipment, software, production software, all the way to include things like volume graphics for CT inspection, data and interpretation and analysis. And so from our point of view, simulation and software generally is a core capability, a core piece of the additive manufacturing workflow. If you call it design for additive manufacturing, being able to leverage let me advance the slide, being able to leverage the ability to take full advantage of the manufacturing techniques of additive manufacturing, be able to find that balance between the design itself as well as manufacturability and cost. And to do this, really, it does require the balancing of the component geometry itself, the orientation, and the support strategy, because each of these three things is interdependent. And so a change of one necessitates consideration for the others. And so what we see really is that this process simulation and design for additive manufacturing tools, they're really just that, tools to enable the design for additive manufacturing process so that designers and additive manufacturing engineers can take full advantage of the flexibility that is offered within additive manufacturing. Now, my focus is specifically on metal additive manufacturing, but the same principles hold true for polymers, nonmetals, as well as for other types of additive manufacturing. If we're talking about powder bed fusion, which is the most, I'd say, most prevalent metal additive technique out there, but this also holds true for direct energy deposition, as well as metal binder jet fusion. We recently released a metal binder jet sintering. We recently released a solution for metal binder jet sintering. And I would say that the DFAM rules are still very applicable, simply that the rules are just a little different for these different techniques or technologies. And so what we're going to do today is just share with you a little bit of kind of our view in response to some of the questions of how simulation and software can come into the design for additive manufacturing process and how it could best be taken advantage of to enable the additive manufacturing technologies to move from a prototyping small scale to a much larger scale mass production sort of environment. Thank you. That's all I have, Ken.
Okay, very good. Thank you very much, Jeff. All right, the next speaker we have is Greg. Greg is from Ultimaker. Greg, I'm queuing up your slide, and I'm going to give you control over the slide while you talk. So your opening remarks and self-introduction for 3 minutes, please.
Kenneth, thank you very much, and thank you to our listeners for giving us a chance to talk about the manufacturing today and how it can be done with additive technologies. You know, Ultimaker is a unique company where we have a mission about additive manufacturing, and it's really about making things where people want to use them. You know, on the left-hand side of that diagram is the traditional factory with raw materials coming in, labor, et cetera, and the finished product is being shipped out to the final location. What we're talking about is there's some amount of engineering work that's done ahead of time. There's a digital inventory of that part, and there's either a local supplier, you know, in this case like Forecast, or there's actual equipment, printing equipment on site that can make that part very near where the part is going to be used. So that digital technology becomes a critical, it's the tool. You know, in traditional manufacturing, the G code becomes the tool in our example. Ultimaker is unique in the sense that we have really focused in 4 areas, and it's very relevant to manufacturing. You know, as an engineer, I was taught that, you know, keys to solid manufacturing is to reduce variability and to look for, you know, areas in the process where you don't have control. So, you know, Ultimaker started from a design point of view, and they made the technology very user-friendly. They created an amazingly simple workflow. We allow our customers to run a wide range of commercial materials, regardless of who the manufacturer of is. So we call that an open material system. And one thing we've really tried to do is the concept of making the printer very easy to determine, is it doing what it is it's supposed to do? So giving the operator some ability to see what's going on, understand the process, but then putting some manufacturing quality into the device where it has a high degree of, you know, mean time between failure and you know, very good reliability. The overall impression is that the device is extremely user-friendly, extremely reliable. That's not always been the case for 3D printers. You know, Ultimaker is approaching this from a complete family of hardware, software. You can try and download Cura at no charge. It's our slicing software. You know, there's over 120 materials at this point, 120 material companies with many more materials from each one of those companies. So there's a very large range of materials. And service and support is becoming a huge part. You know, most customers tell us they want our help in doing more with 3D printing. They want us to help them unlock the return on investment. So, you know, Ultimaker we're a Dutch company. We started making our product in the U.S. about 5 years ago. We've been growing pretty dramatically. We've not added a lot of employees in the last 6 to 9 months, but our revenue has continued to grow, and it's an exciting time at Ultimaker. We're really seeing the adoption of manufacturing with 3D printing technology in a lot of different forms, not just Ultimaker. So, you know, and for some of the reasons you just heard before me, the designing is starting to accommodate it, and that's really the magic combination. So, thanks, Ken.
All right. Thank you very much, Greg. All right. To those who are tuning in for the 3-part Civil War series, I'm sorry, that's a different Ken Burns. We have Ken Burns from Focus 3D. So, Ken, you're up. I'm going to give you control over your slides and you, too, your opening remarks and self-introduction for 3 minutes, sir.
Great, thank you. And yes, that is unfortunate you won't get that documentary today. But I am Ken Burns. I'm the VP of our commercial team here at Forecast 3D. Just quickly who we are, I think for the discussion today, just the context of where our viewpoint is coming from is important. So Forecast 3D is a 25-year-old company founded down in San Diego, California. At the beginning of this year, we were acquired by GK and Powder Metallurgy, who has an additive division, and they're based out of Germany. And so with the acquisition now, you can see on the map there, we are integrated into a global organization for digital manufacturing, really, with a focus on both polymers and metals. So on the polymer side, we have a large install base primarily in Southern California. We have about 60 polymer machines now. And then with the metal 3D printing, we have about a little over 20 now throughout the globe, including China, Germany, and a couple sites in the U.S. On the metal side, we're primarily focused on sintering processes, both with EOS and SLM. And then we are also the metal jet partner for HP, so producing parts off of the new metal jet binder system from HP, and also a material maker, so GCAN. The third leg of the additive side is producing the metal powders. And on the polymer side, we have a large install base of the FDM equipment, SLA equipment, some PolyJet, and then the largest install part of our base is the HP multi-jet fusion, where we have 31 of those printers today. And then just a little bit about who we are through our company here. So I mentioned we are a materials company for one. That's just on metal alloys. So GCAN Powder Metallurgy is the world's largest producer of sinter materials. And with that, they've ventured into additive. So if there's anyone here with additive machines out there, their materials are made for all systems, not just HP binder jetting, but also for EOS, SLM, and many others out there, and lots of different alloys. We offer engineering services, not from product design, but from the design for additive, consulting, 3D scanning, reverse engineering, and so on. And then as most companies that started 25 years ago in 3D printing, you can imagine we're heavy on prototyping, and that is still a very, very large portion of our business today. We continue to focus on the prototyping market and serving that through a variety of technologies, including some conventional manufacturing. And then with production is a more recent venture in the last 3 to 5 years, where the technologies have matured enough where we can actually start going to get into manufacturing. And so we are producing that primarily on the HP multi-jet fusion and the HP metal jet, but we also do production in other technologies like FDM and SLA for certain applications. Just to date this year, we probably printed a couple million parts on the MJF alone, actually probably closer to 3 or 4 million. So we are getting some high volume applications on there, and then a lot of post-processing services with that. And then we are certified in different areas there, ISO 9001, aerospace, automotive, ITAR, and then participating in some of the manufacturing industries out there. So this is just a little about who we are. Hopefully that adds some good context to our discussion today. I'll pass back off to you, Kenneth. Thanks.
Very good. Thank you very much. Thank you very much for all the panelists for doing the introduction. All right, audience, I'd like to get you involved as well. This is a live poll. We'd like to see where you are in terms of using additive manufacturing specifically. If you can help us complete this poll, do you feel 3D printing or additive manufacturing can be used for mass production of uniform parts? So we're not just talking about a mock-up or a one-of-a-kind part that you want to print just to test out for form, fit, and function, but thinking about using 3D printing or AM for the long run for producing hundreds of parts, thousands of parts over a long period of time to fulfill a certain production run. Do you think that this technology is ready for that? You may say yes, you may say no, you may say not sure. So tell us what you feel. Tell us what your impression is at the moment, and then I'll give you a couple of seconds, and then we'll take a look at it here. Let's see where you are. All right, it seems like 78% of the audience, 78% of the audience feels that this is actually ready for mass production, and there are 12.5% of you that says, nope, that's not quite ready, and then a small minority that says, not sure. So Greg, Ken, and Jeff, our job is before the end of the webcast, we need to be able to, when we do this poll again, in the second time around near the end of the webcast, we'd like to see a percentage that is higher than 78%. Otherwise, we have egg on our face, so to speak. So let's start our discussion, shall we? The basic requirements for mass production with additive manufacturing. I'm going to come to you first, Greg, because you're the hardware person. Is there a specific type of hardware that is suitable for mass production and not the other one? So is there a difference between something that you would use for prototyping? All prototyping 3D printers suitable for mass production? What's your thought on it?
So, Kenneth, the answer to your question, there's quite a few technologies that are well suited for production. I'm gonna focus on what we call FFF, fused filament fabrication. Stratasys has a copyright on the name fused deposition modeling. It's very similar types of technology. You're extruding a thermoplastic and building up a part layer by layer. One of the reasons why this type of technology is well suited for manufacturing is, first off, you're dealing with an XYZ type of motion control. So it's a very repeatable, kind of proven type of concept with G code as a programming language. I mean, this is how CNC machines are controlled, and this is how robots are controlled. So we feel it's a very robust way of actually controlling an extruder. And then kind of to take it one step farther, we're working with third-party materials as well as our own Ultimaker portfolio of materials, but they're all based on commercial thermoplastics. So, we're using a PMMA material from Mitsubishi, or, an ABS material from Armor, or maybe a PVDF material from Arkema. So, these types of thermoplastics typically have some limits put on them by other 3D printer manufacturers. We're unique in the sense that we are open and we allow our customers to print these commercially available materials. There's already machined parts and molded parts being made out of these materials. So for an engineer to come back to FFF type printing and do short run manufacturing, bridge manufacturing, it's a powerful way for them to get a very similar part in a very fast period of time.
All right, very good. Thank you very much for this perspective. I also want to come to you, Ken, because you, in a way, also deal with hardware because you are providing services. So do you agree with what Greg had just said? Do you have anything to add to it?
Yeah, I for the most part, I agree. I don't think there's anything that I would contradict in what he said there. I think the thing that most people may not realize who haven't utilized 3D printers, especially in scale, is that while a lot of I actually think most any 3D print technology out there, the hardware, can be used for manufacturing if you set up the right process controls, you have the right people, the quality systems, post-processing, all those things in line with that and with the application. I think the thing that most, I'll say, service bureaus and design bureau print houses do as sort of a disservice to the market, which makes it a little bit of a struggle, is that in prototype you can hide a lot of the flaws, and that's acceptable because when you're printing a handful of parts, 2, 3, 4, 5, 10, 20, you can reprint, you can finish parts, you can get them to look like they're supposed to. But when you start doing things at scale, you don't really have time to hide the flaws of the hardware. So you have to have really good process controls around that to ensure that when you print 1 million of something, they're all good, because 500,000 parts into a quantity of 1 million will be a big problem if there's something wrong with the parameters that were set up inside of it. So I think maybe the thing that's often lost is that while we like to say additive manufacturing reduces time to market and there's no tooling costs and all these things, that's true, but there are still other constraints around that that will enable successful applications there.
All right, thank you very much. Let's bring Jeff into our discussion as well. Jeff, let's talk about the role of the software. It seems like for rapid prototyping, the software has become pretty mature and pretty robust about simulating what will happen when you're prototyping something. Can we say the same thing about the software's maturity when it comes to using AM for mass production? What's your thought on that?
Sure. So there's a lot of aspects that, just as Ken mentioned, you might be able to hide in the prototype environment, but when you get to the mass production, it becomes a little bit more challenging. So some examples of that would be the variability that exists across metal additive manufacturing machines. So within the build chamber itself, from one corner of the plate to the other, or across machines, machine platforms. I often ask a question: if you have two EOS M290s sitting next to each other on the shop floor with all the same parameters, power settings, do you get the same part? The answer is maybe. Well, what about a Renishaw 280 and an M280? Probably not. What about the two machines on other sides of the planet? And so being able to have a methodology to normalize for the same, for the varying conditions across region, geography, across machines, accounting for the variability and the machine drift that often exists within the machines themselves. So typically these are things that were highly skilled, specialized, tribal knowledge, that guy who knew how to dial the knobs just right. And at places that are very specialized in this, the contract manufacturers, the Encodamas and Centavias and Morph 3Ds of the world, these people have incredible amounts of skill and experience, and they're able to make it work. But when you try to take that up to the scale of, GE Aviation or other places where they're doing much larger scale production of the same parts or of varying parts, or if you take it to the model of, let's say, the Department of Defense, who would like to be able to just ship a CAD file to some austere location and 3D print a replacement component out of a Connex container, that becomes a much different challenge. So being able to incorporate the variability to be able to account for that, using the simulation tools to enable that is one aspect that I see is very important. Another aspect of it would also be how to utilize simulation in the loop. And I think I had a brief slide here, just very quickly. This kind of illustrates the process of DFAM and how to use simulation in the loop. And really the important point that we see here is the second swim lane, process simulation, that there's multiple steps where simulation is completed. One is up front in the design process, in the DFAM loop, which could potentially be automated. How do we make that very quick, very efficient, to get to that solution very quickly? And this is also where tools like generative design come into play. Or if we have tools that can automate the process of making a design, optimizing that design, incorporating the realities of additive manufacturing, and then later on also doing a simulation pre-build to confirm the approach, to confirm the specifics, as I mentioned, of that particular machine or platform where it's going to be built, to incorporate that variability. And so these are two aspects that can certainly drive improvement towards mass production on metals. Thank you.
Very good. Very good. Thank you very much. Let's move on to talking about identifying the sweet spot. All the time, it seems like in order to use the technology, you need to identify the right kind of situation or circumstances where the technology is going to serve your purposes. So, Greg, is there a specific kind of purpose or reason why you might want to choose 3D printing? Is there some kind of situations where you look at it and you say, for this engineering job, 3D printing is the only way to do it, no other way to do it?
Yeah, so the best 3D printing applications are around mass complexity, and that's where the cost of machining or the ability to machine or the ability to make a tool and mold either becomes so crazy expensive or it introduces some large amount of variability. The other is mass customization. So there's some of my colleagues on this call have talked about, metal printing. One of the big growth areas for metal printing is in orthopedics, not necessarily of only customized products. Quite a few of the products being produced today are serial devices, and what 3D printing offers is the ability to produce the complex lattice structures. But having said that, the next area for something like dental or orthodontistry is the mass customization. So those are areas where the technology has really taken off, but it's gonna get some help in other areas. And I put up a slide here. This was an example where the original design of this center console was 26 pounds out of aircraft-grade aluminum, and through topology optimization, they were able to reduce that to 8. Now, you may not want to print that out of direct metal just because of the build size, the part size, or the cost of such to do it. But in my experience with additive manufacturing, where the technology has really been most successful is where it provides an interim gap in a traditional manufacturing process. And there's a lot of opportunity there in that statement. So in this example I've got on the screen, you would 3D print a pattern that would then be investment cast out of an aircraft-grade aluminum. And that process is established, known. There's good amounts of engineering data around that. And so all we're doing is replacing the pattern portion of that process and introducing 3D printing to do that better, more efficiently, enable these really challenging designs. So, that's kind of where I see a lot of the technology, help, a lot of the opportunity with 3D printing and where the technology kind of brings a benefit. The other is just speed, just fast. Regardless of what type of technology we're talking about, 3D printing is typically days. It's not weeks. It's not days to get the material in and then, put it in the queue to get some machine time. And while you're doing that, you're finding cutters and, the other tools that are required to machine it. You could theoretically start that job the day you get it, the day you prep that data. There's a whole work schedule you've got to follow within your organization, but that ability to prioritize and just have the technology deliver speed is a really big advantage. And it's going to, for a lot of reasons, economic, mean time between failure, uptime, the pressures that companies have to keep uptime high, all of that is going to keep speed in which you can put a part in a customer's hand, a very powerful driver of this technology.
Okay, good. Also, Ken, I'm going to turn to you. Let's talk about the volume and the turnaround time that the customers are thinking about. So are there specific type of volumes or turnaround time that make sense for on-demand 3D printing? Or are there times when you look at what the customer is trying to do and you have to advise them, what you need to do? For what you need to do, a traditional machining job may be the way to go. What's your take on that?
Yeah, I'll answer this one a couple of ways. I think often people just want to know a simple number and size of a part or something like that to say, hey, this is what additive manufacturing solves. I can tell you from applications that we see and we work with, the easiest way to answer this, a sweet spot is under 50,000 units seems to be a nice quantity of parts, mainly because a lot of parts today just are not designed for additive manufacturing, so you're not getting a lot of the advantages from additive manufacturing that you can. So instead, you're typically just competing against traditional technologies like injection molding or CNC machining. So once you start getting in higher quantities and injection molding, your price point gets so low and the cost of tooling amortizer that's so minimal that it's hard to be competitive there. But there's a lot of opportunity in lower quantities, and there's a lot of applications and products that are produced at sub 50,000 units, maybe even for the life of the product. So I do believe there's a huge opportunity out there for companies to rethink how they're spending their costs on tooling and just say, hey, maybe this is something we do and we change material to meet that. The other side is the sweet spot is really just depends on the problem you're trying to solve. I think we often try to just go at price right away instead of trying to understand the whole scope of the problem. So a simple example I can use is a recent one where we produced over 1 million of the nasopharyngeal swabs for testing, right, for specifically related to COVID. And the cost of those swabs is more than the cost of traditionally made swabs on there. And so will this product be sustainable for years? Probably not. Maybe there's some other optimization that happens over time for us, but really we solved the problem of you needed something now. And Greg just mentioned, right, you can do things fast. And so we can solve problems a little bit quicker and fill a supply chain gap on there. So the sweet spot, I think the simplest way to answer it is it really depends on the problem you're trying to solve. And that could be over 1 million parts. It could be 50 parts, and time constraints will drive a lot of that.
Okay. Jeff, let's talk about the DFAM, or Design for Additive Manufacturing phase, that you brought up a little bit earlier. It seems like in order to take advantage of 3D printing, the geometry of your part or the topology has to be considered. So does that mean that currently the mainstream CAD program that we use, are they ready to go about in terms of the ability to produce the kind of geometry that is suitable for 3D printing, or are we in search of a new breed, a new specimen of CAD programs?
Sure. So the current capability with CAD, typical traditional CAD systems, it's possible to create these different types of geometries to take advantage of the flexibilities of additive manufacturing. It just becomes cumbersome, painful, and time-consuming. And so what we see is the potential to accelerate that process, to also take advantage of a complete exploration of the design space. And so being able to leverage tools such as like a generative design or topology optimization tools to be able to go from your boundary conditions and load cases to explore that complete design space and come up with a number of potential candidate geometries is certainly one way to accelerate that. Now, I don't think today, does this completely replace the CAD and modeling process? No, it doesn't, but it gives us guidance, very fast, accelerated approach to be able to evaluate the designs. And then when looped or coupled with additive manufacturing process simulation, also then gives us the insight as to how that component is going to be manufacturable. And then being able to actually do that in a closed loop process where the generative design and CAD tools can actually evaluate or consider let's say the DFAM rules for overhangs and unsupported areas and things of that nature, which could be parameterizable, being able to evaluate that and incorporate it in the generative design process. And then doing this like I said, in a closed loop architecture to be able to essentially, guess and check in a somewhat smart way, or even in a intelligent AI-enabled approach, really is driving us towards what I think is the future, which is a semi-automation of the design process by leveraging the tools that I just described.
All right. Thank you very much. Let's talk about the new normal, and let's see if additive manufacturing has an important role to play here. So during the early phase of the pandemic, AM stepped up and filled the gap, especially in making personal protective equipment or nasal swabs, when many of the machine shops and overseas facilities become unavailable. So, Greg, is there a unique role for AM to play in these uncertain times that we find ourselves in?
Yeah, so I just pushed up a slide that shows one of the designs that the National Institute of Health had published. So when the COVID crisis broke out, for the first time you had organizations say, hey, here's a 3D printable file that is been deemed safe. And, you had that file just take off like wildfire across thousands of printers in the United States. Ultimaker had a website that tried to connect people who wanted to print these with people who needed them, and and put the two of them in connection with each other. And it's just one example where, for the first week or two, you had a situation where the alternative was nothing, and so this was one example where additive manufacturing stepped up and said, no, we can do better than that. We can keep them safe. It's not cheap. It's not the cheapest way of doing it, but we can do it today and keep you supplied until the regular supply chain kicks in and takes over. The second part of it, and we really haven't talked too much about it, but this was an advertisement that was run in Detroit, not far from some of their major manufacturing centers. But it's basically stressing, like, who wants to wait? We all got burned when the supply chains from overseas shut down. And if you were any type of manufacturing company, you probably depended on something from China that in the early days of this pandemic, it affected you. You know, you either had something that was idle because it was waiting. You know, you heard about these crises with ventilators where you had people 3D printing, you know, the splitters for the ventilators and other, you know, manifold type parts. So, you know, what we've experienced is 3D printing has really stepped into, you know, kind of a critical like gap, which is, you know, traditional manufacturing just could not respond that fast. And eventually did it? Yes, it did. And it's doing so today very well. But that 2 or 3 week period where it was caught flat-footed, that's where additive manufacturing and all the investment that people have made in the capacity out there, that's where it really kind of showed its ability to just quickly come online. And again, it goes back to that ability of, you know, an industry file getting presented and adopted. That digital tool created the gateway, you know, for the 3D printing world to start making PPE to keep people safe. So, you know, and it just keeps on going with MRO. So it's an exciting time for our industry. You know, the thing that really became aware as we work through this is there's some gaps with what's required. And, you know, we've talked a little bit about it, but we recently introduced software that helps you take out the guesswork of 3D printing. So if you know what the requirements are of a part and you're able to define those load requirements, those stress requirements, then we have some simulation software that can actually give you predictive suggestions on how to orient the part, where it's going to be weak, where it's going to be strong. And so these types of plugins, this is one done by Teton, that you know, really kind of make it easier for an engineer to figure out, hey, listen, what can I expect out of this? You know, and the reality in all these CAD packages, finite element analysis, you know, all these types of tools are starting to get embedded in a regenerative design. So it's kind of an exciting time for all of these tools to get a chance to get implemented. You know, it's going to create more additive manufacturing applications for sure.
Very good, great. Ken, I want to bring you into the discussion here as well. So it seems like there are some industries that might have discovered 3D printing because of the pandemic. Going forward, are there certain kind of applications or certain kind of industry that may actually just go ahead and permanently switch to 3D printing now that they have discovered? What are your thoughts?
Yeah, that's a big question there. I think sometimes when you're in the middle of something, it seems like the easy answer is yes, they'll replace and switch to it. I think when you get to the other side of it, you see some of the strengths and weaknesses of the additive manufacturing technology versus the traditional technologies. What is it really solving for? I think you'll see more companies utilizing it in the right way. And where Greg is just saying, you know, there are shortages. So how do you have a digital asset for that product for emergencies or shortages, or when you don't want to keep a higher stock? Or how do you begin your product design with the consideration that I'm going to mass produce this at first, but then when the product goes end of life or spare parts, I want to have an asset that's already qualified for additive manufacturing. So you're qualifying something maybe for injection molding and AM at the same time when you're launching a product there. So you have this. And this works well in certain industries like aerospace, where they might need more parts at the beginning and tooling makes sense, but it doesn't make sense 20 years later when you have a jet still flying and you only want to make 10 parts a year. Or even automotive, where a lot of these vehicles, the typical suppliers have to sign contracts so they're holding stock of these parts for years after they're done producing that vehicle. So I think you'll see more of a combination of these things, and that's, I think, using additive in the right way for some of these industries. And then there's certainly products that different companies will realize it just makes more sense in additive. And I think the main things to ask are, you know, what's the problem you're solving there? So having the right combination of the materials available, supply chain, challenges and the cost all make sense. It's no different than why people choose CNC over injection molding or vice versa. It's those processes are chosen because there is a clear reason of why it makes more sense. And I think we're seeing more of that now, and companies realizing that if they're not utilizing additive or not scoping out in some of their programs, then they're probably missing out on an opportunity or putting themselves at risk.
All right, Jeff. I want to think about. I think about additive manufacturing's shift from prototyping to mass production as a sort of like a graduation. So when AM graduates in that sense, how does it change the role of the software?
Sure, Ken. Let me think about that. So I think that it's an evolution. The role of the software is an evolution. As some of the prior responses you got, it's the changing landscape and capabilities of the software are attempting to keep up with the demand and keep up with the technology. And so we're really, evolving quite quickly, and the capabilities of the software tools to keep up with the technology, right? If you just look back a few years ago, the feasibility of even simulating the build of large-scale metal additive parts was beyond the limits of what's practical, right? They just, the objective 4 or 5 years ago was just, okay, we need to simulate it faster than the physical build. Now we're orders of magnitude faster, and now it's on to the next thing. And so I think in this case, what we're really looking to do is how the software can enable the designer and the additive manufacturing engineer to achieve that desired outcome in a way that's efficient and cost effective and gets us to the right answer, not just from a part that we'll build, but from that right balance of a part that meets the design intent, works well within the overall system, but also is easily manufacturable, low risk to the manufacturing, but also optimal cost, and can be produced in an amount of time or in a way that is not prohibitive or is feasible. And then beyond that, being able to do it in a way that is as automated as possible. I see that really as being one of the big drivers going forward. How do we automate the process of design, and then of getting from this initial design to a feasible, robust design that can be built, preparing for that build and post-processing, and then moving through those steps. And so I believe that the graduation per se will be to enable that shift, to streamline the process, and to enable the designers to go through the workflow much more quickly and efficiently.
Okay, very good. We are right on time for Q&A, so we're going to move into the Q&A. But before we do that, the audience, I'd like to remind you that at the end of this event, you'll get a survey. If you can fill out that survey and tell us your impression of the event, we'd be really grateful. That helps us improve the format, the way we tackle issues, what kind of topic you're interested in us hosting about, so that'll be very helpful. Also, don't forget the resource list. The resource list gives you a lot of additional details, things that we wouldn't have the time to cover live in the resource list, so you can take a look at case studies and specific specs. Okay, let's take a look at the questions that are in the queue here. The first question is the importance of the maturity of post-processing techniques and equipment in 3D printing. Not really a question, but I think somebody wants us to address that. So let me go to Greg first. Greg, are there any specific problems that you need to deal with in post-processing, and how are the hardwares handling it at the moment?
Yeah, so I answered this, that post-processing is getting a lot of attention with regards to 3D printing. And, that's not unusual in manufacturing. I mean, technologies like tumbling and, finishing and bead blasting, these have always been part of traditional manufacturing. But when you're doing one or two, things like a file and sandpaper are perfectly acceptable because it's quick, it's direct, it's low tech, and it works. But when you start doing, tens, hundreds, thousands of something, and you're following a drawing or a specification, then you've got to have a process that can, achieve some level of a standard. So, and that's really where you're seeing, companies invest in different post-processing technologies that either, smooth parts through like vapor polishing or tumbling. You are seeing them color parts either through dyeing or through some kind of color impregnation process. You're seeing the plating of parts to get some type of either chemical resistance or electrical conductivity. So there's a lot of different, post-processing that's happening to try and get the 3D printed part to be a good fit for the application. And it's only going to get more. If you go into any good manufacturing company, you're going to see that there is an amount of post-processing that always is involved. Every company wants to do as little of it as possible. It's a variable, but it's a necessary evil. And so the more we apply things that can measure it, can use standards, can reduce variability, it's just gonna help 3D printing get through that learning curve of getting to a finished product. So I'll pass it back to you, Ken.
And Ken, if I could jump on that as well, from that standpoint, there's also a role of design and simulation that's involved here, right? How you build the part, how you design the part should also consider the potential, the requirement rather, for post-processing, right? Where are you going to design the part to have supports or not have supports? Would you, make a trade-off to reduce the post-processing that might increase the mass or something to that effect? And so being able to also consider how you're going to fixture a part for, let's say, for machining. If you have these organic kind of, generatively designed components, they don't lend themselves to being fixtured easily in a vise, or in a clamp to be then subsequently machined on the critical faces. So these are all things that need to be considered during the DFAM process as well. And this also ties back to the requirement or the importance for metrology. As I mentioned, MSC, we're part of Hexagon Manufacturing Intelligence, and we see that the design, engineering, and metrology are critically linked, right? As I like to say, the link between the physical and the virtual is metrology. That's how you know what you got, right? That's it.
That's a very good point. Yes. Ken, I want to bring you into this as well because I have a question for you. For post-processing, if some kind of support structures need to be removed or some need to be dissolved before it can be actually implemented in an assembly or something like that, is that something typically a service provider would do, or do you ship it and expect the customer to do it? Could you talk about that?
Yeah, no, it's certainly something that we're expected to do on there, especially for manufacturing. I think in some cases with prototyping, we do some to the customer because they might have a small print shop internally. But I'll echo what was just said about those guys. I think a really big part that's often not considered is the design for the post-processing as well. And we do the same thing that Jeff was just saying. Like sometimes we will increase the mass on a part or make it less efficient in the build, but incrementally more efficient in the post-processing. And this is the disconnect, I think, often that happens and why a lot of products are unsuccessful in additive manufacturing is because you really often it's really optimized for the printing and you get this really cheap part out of a printer and then it's a mess in post-processing or you can't measure the part very well and you don't do any considerations there. And so it's been discussed a lot, but really the success of post-processing takes place a lot on the front end of a lot of the simulation, the design aspects, how it's going to go through there, what finishes are required, what you're going to do for quality so you can reduce as much touch as possible. And then the other part of it is a lot of post-processing equipment today hasn't been optimized for additive manufacturing. Like I said, in conventional methods, it's really well done, but equipment can be really expensive and doesn't always yield the exact right result. So there's additional steps on top of it. And so there's a space right now where there's definitely a need and there's a lot more attention on post-processing to really dial that in to get competitive with conventional or traditional manufacturing processes. But I can tell you from our side, it's one of the biggest focuses we have is a lot of resources spent in the post-processing side.
All right. Let's take the next question here. When can we expect to see 3D printed tooling steels become available? Maybe we should start with you, Greg. So is steel generally a material that you can print with in your hardware offerings? What's the difference between printing in metal, printing in steel? Is there a difference?
Well, steel is a generic name for an alloy or a class of metal. The reality with the type of 3D printing we do, when I say we, Ultimaker, so we will work with a company like BASF or Virtual Foundry, and we are able to print a composition of metal and plastic. So we essentially print a green part. That part then has to be debound and sintered to make a finished metal part. This is not typically something that's easy for a normal manufacturer to achieve. So it's not something that doesn't fit with my slides of, easy to do and, very push button friendly. It's in the realm of, you have to have a lot of expertise to do that well. But then jump to the other side of it. You've got technologies, Forecast having, quite a bit of it that is ideally suited for not only printing tool steels, but a whole range of other alloys, including, reactive metals. So 3D printing as a scope has a lot of ability to do, steel and tool steels, stainless steels. But, specifically for the FFF type printers, I think it's still fairly early stages. And, I would put it in the realm of it's possible. You just need to be willing to do some experimentation to achieve success. Maybe my colleagues have more to add to that.
Yeah, Ken.
I guess I can give my perspective from, although this isn't a simulation question, I frequently work with customers who are, they're building parts. And so from the powder bed fusion side, absolutely, people are using things like Maranging steel or a tool steel's H13 and similar. There's a lot of development of new alloys. And so this is something that's very common. And then also on the metal, bound metal, and bound sintered metal tooling is another interesting topic. Although much of what's been published out there is around 316. I think companies like X1 have already showed that they're working on or have the capability to do bound metal sintered components in these tool steels as well.
Very good point. The important part of the material characteristics. Yes. Ken, do you have anything to add to this?
Yeah, I'll chime in a little bit here. Unfortunately, this would be a better question if my GCAN counterparts were on, since they are all metals people. But the short answer is there are a couple of tool steels available now. And I think the difference between just asking for is a tooling steel available is what from the tooling steel is why you need that material, because with additive, you can now create new alloys, or we'll call them like hybrid alloys that you can do different things with because it's a different manufacturing process. So I think it drives more towards the application, and can you solve that application with maybe a material that doesn't exist in your conventional way of making it. But if you need that exact same material, often we can do that. This is what we do the GCAN side, and there's a plant in Cinemaston, New Jersey that just creates new alloys and then creates the parameters with the different technologies that they're going on, whether it's a EOS machine or binder jetting or SLM. So I would say the limitations are typically more with the hardware. Can the hardware actually meet the requirements of that new material, whatever the specifications are, to sinter it or bind it, whatever it might be. But in short, I mean, what's the problem you're trying to solve with that material? And maybe there's a better way to do it with additive.
All right, very good. Let's take one more question because we are kind of starting to hit the end of the hour. There is something about the optics. How many designs and optics are being converted from traditional milling and molding into additive manufacturing? Ken, maybe you can start us off with it. Do you tend to get that kind of job in your line?
I know there is some. I could not tell you with the slightest bit of actually what number of jobs are being converted from traditional to conventional. I mean, if you just want to take general numbers of what's being converted from traditional or conventional stuff to additive, it's probably like less than 0.5% of 0.5% of 0.5%. I mean, you talk about an industry that's $13 trillion manufacturing, and right now additive's barely a speckle on that. So I would say there's not a ton. I think the I would say the only industry, or maybe there's two industries that have really converted and almost completely, is that dentistry, simply with like aligners and then some other dental products, and hearing aids. Outside of those industries, I haven't seen, maybe Jeff or Greg have seen more there, but that have really done mass conversion to additive manufacturing or digital manufacturing there. So I don't have a specific answer there, but if you want to use parallel industries, it probably gives you a good indication of where some of those are at. I think it takes really the business case to help drive some of that forward.
All right. Oh, good. Jeff, maybe rather than specifically about optics, talk about the role of the software. Do all simulation software work the same way, or do you need a domain-specific kind of simulation for additive, for example, dental simulation or that kind of specialty?
Sure. So I think that it's more so specific to the individual types of additive manufacturing. So if you look at metals versus non-metals being the first most obvious differentiator, there's tools out there, like the tool that I work with, SimUFect Additive, which is great for metal powder bed fusion. And then we have a sister company that does it for non-metals, Digimat AM, and being able to do pretty much any type of non-metal additive manufacturing process simulation. Beyond that, being able to do different types of metal additive manufacturing, specifically looking at powder bed fusion as one, direct energy deposition process simulation as another, and then bound metal sintering. I know Ken was talking about the HP metal jet process, being able to actually simulate the sintering process to evaluate the shrinkage, distortion, slumping, etc. That's something that we can do today as well. And so being able to really depends on the type of process. That's the main driver. Not so much the application. You know, if you're building a dental part versus an aerospace part versus, whatever, it doesn't really matter. It's, metal is metal. Plastic is plastic from that standpoint, but it's much more about the process that you're actually going to want to simulate, whether it's the additive process, but then also very important, the post-processing as well. Thank you.
All right. All right, very good.
Kenneth, if I could add something to that.
Sure.
I think it's relevant to our discussion because as engineers or as manufacturing folks, over the last 25, 30 years, there's been a huge move of replacing metal with plastic. And so, there's no exception here. As we get 3D printing and additive manufacturing more into the hands of actual manufacturing engineers, people running factories, you are going to see the replacement of metal parts with 3D printed, nylons that have carbon fiber in them, or even higher end plastics, that have higher temperature capabilities. So, that's not a trivial movement in overall like manufacturing and engineering. If you think about like weight engineering in an automobile, the plastic's insignificant. All the weight's in the metal. So if you can convert something from metal to plastic, you're going to get a dramatic weight savings. The question is not trading off strength or functionality. So that's something that is, it's part of the dynamic of our industry.
That's true. That's a very good point about the lightweighting trends that is going on. Thank you very much. All right, audience, as promised, I'd like to do the poll one more time to see what kind of job we did in our conversation. So please, if you will, now that you have heard all of us talked about AM's transition, help us complete this poll again. Do you feel 3D printing or additive manufacturing can be used for mass production of uniform part? Yes? No? Not sure? How do you feel about that after you have heard about our arguments and our presentation and the panelists' point of views on it and address some of your questions that you have? So let's take a look at your answers. All right, gentlemen, I think we did a wonderful job. We were trying to beat the 78% we got in the first poll, and it seems like right now we're getting 100%. So good job, everybody. I have only one more minute left, so maybe very quickly, just if you can give your closing remarks or last words. Jeff, let's start with you.
Sure. I just want to emphasize the importance of design and simulation tools within the DFAM workflow. It's just that. the tools are tools that enable us to get to the right answer. And it's how we use those tools in the workflow and where we incorporate it in the workflow that can make the biggest difference. Thank you.
All right, very good. And then, Greg, your last word, sir.
Yeah, if anyone on this call is interested in exploring 3D printing, Ultimaker is an excellent entry-level technology. Download Cura software from our website for free. You can start orienting your STL files. You can always send those off to companies like Forecast for printing. But for a $2,000 to $10,000 device that can compete with machined, like parts in many cases, it's a powerful manufacturing tool.
Very good. Ken, you have the last word, so to speak, before I thank the audience.
All right. Well, I just encourage anyone out there who's looking to really go into manufacturing with it that it's a partnership these days. You can't really do anything on your own. So there's everything from the hardware to software to the right manufacturing partner to make sure you're engaged with on all fronts there to have really successful products. So engage.
All right, very good, wonderful. To the audience who have spent their precious moment with us, I want to thank you for your time, and I'd like to thank Hexagon, MSC Software, Focus 3D, and Ultimaker for sponsoring and making this live discussion possible. Until the next episode, I'm Kenneth Wong for Digital Engineering Magazine, and we are out.
Thank you.